recording. What is it when it goes in your nose or your mouth when you start to take a breath? It's air, right? That's what we breathe. Air. So next question is, what is air? Well, air is a bunch of things. Mostly it's a mixture of gases. So these gases, and if you look at the gases, these are the gases that make up air. Well, the most common gas in air is nitrogen. Nitrogen makes up about 78% of the air. And we don't do anything with nitrogen. It's inert to our lungs. It's basically inert. It goes in, it comes back out. Goes in, it comes back out. We don't change it, we don't use it, we don't do anything with it. It just goes in and comes back out. We also, though, have these gases. And these are the gases that we're going to be most concerned with. So the second biggest contributor gases is oxygen. It's about 21% of the air. 21%, which is a lot of oxygen. We're really, really fortunate we live on a planet with so much oxygen because we use oxygen like crazy. We use oxygen in order to make ATP. And without oxygen, we cannot make very much ATP. As a byproduct of making this ATP, we create carbon dioxide and it gets breathed out. But there aren't enough animals, there aren't enough anything on the earth to create a lot of carbon dioxide. So the amount of carbon dioxide in the air is tiny, tiny. It's about 0.03%. Now it is going up because when we burn fossil fuels, we also create carbon dioxide. And we know about some of the problems that are associated with that. Hopefully you've heard all about climate change and so on. But we're going to ignore all that for right now. And we're going to concentrate on what we do with these in terms of respiration. Now, there are other things in air too. There's pollutants, there's all kinds of things. There's other gases like helium and stuff like that, water vapor. But in general, it's not very much, and we're not going to spend any time talking about it. These are the only two things that we're going to really worry about. But if you've ever looked at a periodic chart, you've had any kind of chemistry in your whole life and you've looked at a periodic chart, you know that these gases have mass. You look at nitrogen, it's 14. If you look at oxygen, it's 16. It has mass. And when gravity acts on mass, it produces weight. So whatever your body weight is, it's because the amount of mass you have is being acted on by gravity. And it creates weight. And weight, the more weight it is, it feels heavy. So picture yourself, I don't know, laying in bed. Here you are laying in bed, and someone starts piling blankets on top of you. Well, the more blankets they put on top of you, all of these blankets have mass. They all have interact with gravity, and they're all going to produce weight. And you're going to feel that weight. It's going to push down on you like pressure. Well, air does the exact same thing. Air piles up in layers around the earth, almost like blankets. And so when you look at this air piling up, piling up, piling up, the more air that's on top of you, the more weight, the more pressure. Well, we can measure that pressure. We use something called a barometer. Here's a barometer. It's a very simple device. All a barometer is a liquid. There's some sort of liquid in here. There's a tube with a vacuum in it that's inverted in the liquid. And what happens is the weight of the air pushes the liquid up the tube. Well, you could use any liquid you want. You could use water, you could use milk, you could use anything you wanted to. But if it's something like water, you're going to need a really, really, really long tube. But you can do it with water. If you want to have a shorter tube, you're going to need a heavier liquid. And the heaviest liquid we have on Earth is mercury. And so to standardize it, we use mercury. And so if we take a tube 1 millimeter in diameter, oops, not mercury, 1 millimeter in diameter, and we put it in mercury, put a vacuum in it, air pressure will push mercury up that tube. Well, if we're at sea level, in other words, the lowest you can get on Earth, sea level, you get the most air on top of you. The pressure at sea level is 14.7 pounds per square inch. In other words, it's like if you had laying here in your bed, like we said, and someone piled 14.7 pounds of blankets on top of you. They would push down on you. They would create pressure. And that's exactly what happens. And that pressure will force mercury up this 1 millimeter tube. It'll force it up that tube a height of 760 millimeters. So in other words, 14.7 pounds per square inch, that weight will push the mercury up the tube 760 millimeters of mercury. So that and that are the exact same thing. 1 millimeter of mercury is called a torr. So 760 millimeters of mercury is 760 torrs. And that is also called 1 atmosphere. So every one of these units are exactly the same. Does that make sense to everyone? So if we pretend this is sea level, how much weight is being pushed down on you at sea level? 14.7 pounds per square inch. If we measure that in a barometer, what measurement do we get? 760 millimeters of mercury, or torrs, or 1 atmosphere. Does it make sense? All of these are exactly the same. But look at this. If this is sea level, it's got this much air on top of it. But what if I don't want to stay here? What if I go over here? Am I going to have more air on top of me or less air? I'm going to have less. Less air, I'm going to have less pressure. So there's going to be 14.7 down here. But here it might only be 12. Down here it's going to be 760 millimeters. But here it might only be 720 millimeters. And if I were to climb all the way up here, would it be even more or less? Even less. So it wouldn't be 12 or 14. It's going to be, I don't know, 10. And it's not going to be 760 or 720. It might be 680. But the further up you go, the less air there is. And if there's less air, there's less air pressure. It's kind of like this. Look, if I stack up a bunch of people, this person on the bottom is going to have all of this weight on top of them. The pressure is going to be very high down there. But just this very next person, is the pressure going to be higher or lower than this one on the bottom? It's going to be lower. And if I go to the next person, it's going to be lower. And if I go to the next person, it's going to be very, very little. The same as here. Look, down here, there's more air. But as you go up, there's less and less and less and less air. And so if there's less air, there's less pressure. Does it make sense? Everybody understand what air pressure is? So again, another picture. Here's sea level. So what is the pressure at sea level? 14.7 pounds per square inch. Or what else? What's the pressure? 760 millimeters of mercury, or 760 torrs, or 1 atmosphere. But look, as I go up this mountain, there's going to be less and less air above me, less and less air pressure. And look, if I'm an airplane, most airplanes fly at about 35,000 feet. 35,000 feet, that's what they fly at. Well, look at how much air there is right there. Not very much. So remember the last time you got on an airplane? At the beginning of the flight, remember the airline attendants, they do this talk, and one of the things they say is, if we lose cabin pressure, what's going to happen if we lose cabin pressure? Hopefully everybody in here knows what's going to happen. Something's going to fall out of the ceiling, right? A mask for you to put on your face. And that mask has oxygen in it. The reason why you need that supplemental oxygen is because if you are at this level, there is just not enough air for you to breathe. There's just not enough. And so to prevent us from dying when we're in an airplane, we pump air in there. We pressurize the airplane so it looks more like this, so that there's more air for us to breathe. So if you think about it, as you climb a mountain, there's less and less and less air. Look what Mount Everest is. Here's the airplane at 35,000 feet. Look at it. It's way up there. So can you just climb to Mount Everest without any problem? Is there enough air for you to breathe? So what do you have to do if you're going to climb to Mount Everest? What have you got to carry with you? You got to carry air. That's right. You got to carry oxygen. Does it make sense to everyone? And then look, if you were to go even further, like out into space, you go out there, there's zero air. There's no air. And so obviously there's no way for you to live out there unless you carry your own oxygen. So look at this. Here we are, and here is where airplanes fly at. Look at the amount of oxygen that's available to you at that level. And look how much oxygen winds up in your blood at that level. So if you don't put that mask on your face, very quickly, what's going to happen to you? Any idea? The first thing that's going to happen is you're going to pass out. And not long after that, you're going to die from suffocation. So if something does happen to this airplane, the pilot now has a job, and his job is to bring the plane down to the point where there's enough air for you to breathe. And so they bring the plane down to about this level, about 10,000 feet. It's still not like it is at sea level, but look, there's enough air for about this much amount of your blood to have oxygen in it. And so you can survive pretty easily. Make sense? Any questions? So look, here's where we fly. But guess what else flies at that same level? How is this possible? Have you ever seen a bird with an oxygen tank? How is it possible that birds can fly at the same level that airplanes do? Well, it's possible because birds have more efficient lungs than humans do. Birds can actually breathe and get enough air, oxygen, out of this amount of air. It's incredible, actually. We have the opposite problem if we go underwater. Look, here we are at sea level. Remember what the pressure is at sea level? How much weight is there of the air at sea level? Right here, 14.7. Or what is the number? 760. You need to remember this number. Millimeters of mercury, or 760 torrs, or 1 atmosphere. That's at the surface of the water right there. But if you dive down, not only do you have all this air on top of you, now you've also got water on top of you. Which one's more dense, water or air? Which one's heavier? Water or air? Water is much more heavier. And so if you look at this, when I swim here, not only do I have that air, but I've got this much water. If I swim here, not only do I have that air, I've got this much water. It's a lot more dense. For every 33 feet that you go down, we add 1 new atmosphere of water, of pressure. So remember right here it's 760. But when I get here, it's 1520. If I go down another 33 feet, it's 2380. Look, if you took a balloon and you push it underwater like that, look what happens to it. the pressure pushes on that balloon just like it pushes on you. And look what happens to the balloon. All of the molecules of air in the balloon get squished closer and closer and closer together. And the size of the balloon shrinks. By the same token, if I take this balloon up, there's less pressure pushing on it. And as less pressure pushing on it, the molecules aren't squeezed together as much. And so the balloon gets bigger. And if I were to let this balloon go on up into the air, it would get bigger and bigger and bigger and bigger until what do you think would happen to it? It would pop. Well, our lungs are a little bit like balloons. And so the same thing happens here. If you go diving, it happens to your lungs. Make sense? So if you happen to have a bubble in your blood, down here, the bubble is very, very, very small. But if you come up, look what happens to the size of the bubble. And the bubble can get so big that it can create things like hemorrhages. And so people who are skin divers or scuba divers have to worry about these bubbles. And so they need to come up slowly so that things can equilibrate. Otherwise, you get something called the bends. Any questions? Okay. So, in order to understand how these gases work, we kind of have to talk about some things called gas laws. And so, it's just basically about how gases behave. One of these is called Dalton's law. So look, if I put gases in a container, they bounce around. They don't sit still, they bounce around. And they hit the walls of the container. They create a pressure on the container. And if I attach a gauge to it like that, I can measure the pressure that's in that container. So if I look at this single gas, I don't know what it is, but it's one gas. They're all blue and they're all bouncing around in here. And if I look at this, this is how much pressure that gas produces. It makes sense? 159 millimeters of mercury. I put a gauge on here, it's going to go to 159. If I take a different gas and put it in a container, so here's a different gas. Look, they're all yellow. And I put it in, and look, there's more gas in here than there is in here. So if I'm going to have more gas, I'm going to have more pressure. That makes sense to everyone? In other words, it's like filling up your tires on your car. If I pump more gas in there, it's going to make the tire press harder. And if I use a gauge, I'm going to see a different pressure. So look, this pressure is not 159. It's 593. Does that make sense? Any questions about that? So look, if this was what was the pressure here? Do you remember? What was it? 159. What was the pressure here? 593. Well, I want you to guess what the pressure would be if I put these two gases in the same container. Look, the pressure from still going to be 159. And the pressure from this is still going to be 593. So if I want to know what the combined pressure is, all I have to do is add them together. And that is 752. So the total pressure of these two gases, the total pressure is 752. Does that make sense to everyone? So the total pressure is this, and that total pressure is due to these two gases. So the partial pressure of this gas is 159. What's the partial pressure of this gas? 593. So all Dalton's law says is this, that the total pressure is the sum of all the pressures of each gas. So what was our total pressure? What was it? 752, which is the sum of this pressure, which is oxygen, partial pressure of oxygen, which is that, plus the partial pressure of this gas, which is nitrogen, that. So 752 equals 159 plus 593. Does that make sense? So what if you were only given this one and this one? So what's the total? It's 752. The partial pressure of oxygen is 159. How would you figure out the partial pressure of nitrogen? All you do is take 752 and do what? Subtract 159 and you get what? 593. Does it make sense? Any questions about it? And then Dalton's law says that this amount is equal to the same thing as the percent of the gas in there. Look, this is 78% of this total. And I write it in another place. This is 78% nitrogen, and it's 21% oxygen. So look, the pressure that's contributed by these is the same as this. So 78% of this is equal to nitrogen. 21% of this is equal to oxygen. So if I take 752 and I multiply it times 78%, guess what I get? I get this, 593. So if I take 752 and multiply it times this, I get 159. So Dalton's law makes it easy for us to figure out partial pressures. All we need to know is what percent the gas is and what the total pressure is. So if I know that, remember all the way back here, that oxygen is 21% of the air, 21%. If I'm at sea level, what's the pressure? Do you remember? What's the total pressure at sea level? 760, right? So what percent of this 760 is contributed by oxygen? All I do is take 760 and multiply it times 0.21, and I'm going to get about 159. How would I figure out, and that's the partial pressure of oxygen, how would I figure out the partial pressure of nitrogen? What would I do? I would take at sea level, what is it at sea level? 760. What am I going to multiply it times? What am I going to multiply it times? 0.78. And I'm going to get 590, or yeah, 592. What about the partial pressure of carbon dioxide? What's the total pressure? 760. What am I going to multiply by? 0.03%. I've got to move the decimal point, so I'm going to multiply it times 0.0003. And I'm going to wind up with about 3 millimeters of mercury. So, all Dalton's law is it's a way for us to figure out these partial pressures. Well, the reason we're interested in the partial pressures is because we're not interested in nitrogen. We're not interested in the total. We're interested in how much oxygen there is, or how much carbon dioxide there is. So that's what Dalton's law is all about. So if we look at this, here it is at sea level. There's the 78% nitrogen. That's the partial pressure of nitrogen. 21% for oxygen. That's the partial pressure of oxygen. 0.03% for carbon dioxide. That's the partial pressure of carbon dioxide. And if I add all of these together, I get the total pressure. So if I'm at sea level, that's what it is. But look, what if I go up on a mountain? Here's the total pressure at sea level, but what's the pressure right here? Somebody guess. I don't know what it is, but let's just guess. Is it going to be bigger or more or less? It's going to be less. To make it easy, let's say it's 700. Well, the air is no different here than it is here. It's just less air. There's just less. So if I want to figure out what the partial pressure of oxygen is right here, that's the total, 700. I'm going to do it exactly the same way. But instead of putting 760 here, I'm going to put 700 here. The percentages don't change. But the partial pressure is going to change because the total pressure changed. So if I take 700 and multiply it times 21%, I get not 160, but 147. So partial pressure of oxygen at sea level is 160. But just going up this mountain, look, it dropped to 147. If I go up a little higher, Is there going to be more air or less air? More pressure or less pressure? There's going to be less. So to make it easy, let's just say it's 600. So how am I going to figure it out now? It's not going to be 700 here. It's going to be 600 here. And it's not going to be this number. It's also not going to be this number. If I take 600, the partial pressure of oxygen here is only 126. What do you think it's going to be here? See if you can figure it out. Let's say it's 500. What is the partial pressure of oxygen going to be on top of that mountain? How are you going to figure it out? Remember, this number does not change. What changes is this number. So what would the partial pressure of oxygen be up here? 104.5. So the higher you go, the less oxygen there is. Now there's also less nitrogen and less carbon dioxide, but we're not so worried about that. We're worried about oxygen. Make sense? So that's what Dalton's law is all about. It allows us to figure out partial pressures. And partial pressures are important because we're not so interested in the total. We're just interested in these two gases, oxygen and carbon dioxide. And so we're going to talk about partial pressures of oxygen and partial pressures of carbon dioxide. Now at sea level, this is what those are. But again, as you go up, the numbers are going to go down. They're going to get smaller and smaller and smaller as you go up this in altitude. Okay, there's another law. This one's called Boyle's law. And this is actually a GIF. So if you look at it on your PowerPoints, you'll see it moving. But here's what Boyle's law says. Boyle's law says that if I put a gas in a container, it's going to exert a pressure. Remember, they're going to bounce around and they're going to hit the walls and they're going to hit this and I'm going to get some pressure. Let's say this pressure is 5. I don't know what it is. But here's what Boyle's law says. Boyle's law says if I take this chamber and I put a plunger on it and I push down on the plunger, look what happened to the volume. The volume went down. But if I count how many molecules there are in here, and I count how many molecules there are in here, they're exactly the same. That didn't change. But look, there's less room. There's less space for those molecules to occupy. And so they're going to hit each other more often. They're going to hit the wall more often. They're going to hit my gauge more often. And so the pressure is going to go up. In other words, there's a relationship between volume and pressure. And if I decrease the volume, just like we just saw here, what happened to pressure? If I decrease the volume, what happens to the pressure? Pressure goes up. Anytime you decrease the volume, automatically you're going to increase the pressure. What happens if you do it in the opposite direction? What happens if I take that plunger and pull it back up? What happened to the volume? Volume what? Volume went up. So automatically, what's going to happen to pressure? Pressure's going to go down. Exactly. That's all Boyle's law says. Now you have to keep the temperature constant, otherwise it won't work. But Boyle's law just says there's a relationship between volume and pressure. And if I increase the volume, pressure goes down. If I decrease the volume, pressure goes up. In other words, it's an inverse relationship. It's another picture, same thing. But this one's got numbers on it. Look, the volume is 1 liter. And right now the pressure is that. But if I decrease the volume down to 1/2 liter, what happens? This is going to increase by the same percent. This decreased by 50%. That's going to increase by 50%. If I do it in the opposite direction, look, here it was 0.5 and this was 200. If I pull this up, look, I'm going to increase the volume by 100%. I'm going to double it. Look what happens here. I'm going to decrease the volume. I'm going to half it. So you get this equation right here. Now you don't have to worry about this equation if you can remember the relationship. What is the relationship? If you increase the volume, automatically what happens? You decrease the pressure. If you decrease the volume, automatically what happens? You increase the pressure. It's an inverse relationship. Does it make sense? Any questions about Boyle's law? No, same thing. Look, again, there are numbers on here. And those numbers make it easy to understand what's going to happen. If I decrease this to 1/2, I'm going to increase the pressure to 2. Same ratio. All right, let's look at another law. This one's called Henry's law. So Henry's law says that if I have a container and it's got a liquid in it, like water or something like that, and it's an open container, look what happens. All of the gases out here are bouncing around, bouncing around, bouncing around. And every so often when they bounce around, they're going to hit the surface of the water. And sometimes when they hit the surface of the water, they're going to become dissolved in the water. And so there's going to be an equilibrium that's set up between the amount dissolved and the amount not dissolved. It's going to be an equilibrium. And it's going to stay that way unless I change the pressure. So look, here's my equilibrium right here. Here's an equilibrium. But look what happens when I push down on this. We already know from Boyle's law that if I decrease the volume, what's going to happen to the pressure? It's going to go up. We know that from Boyle's law. But look what else happens. These molecules have less room, which means they're going to hit the water more often. It means that more is going to become dissolved. And so I'm going to wind up with a new equilibrium. But look, there's more dissolved than there was over here. And that's because of the pressure here versus here. So what Henry's law says, if I increase the pressure of the gas over the liquid, more will become dissolved in the liquid. Does that make sense? So what if I wanted to make this gas go into the liquid? What if I wanted the gas to go into the liquid? How would I make it go in there so that it looked like this? I would increase the pressure of the gas. And that would force the gas into the liquid. That's exactly how we make sodas. So look, think about a soda. It's got lots and lots of these gas bubbles in it. How did they get in there? They got in there just like this. So what we did was we took the gas that we wanted to put in there, and the gas they use is carbon dioxide.
Motion detected at the front door.
And we increased the pressure of that gas over the liquid, and it forces the gas into the liquid. And so we force the gas into the liquid, and it winds up looking like this. So all those little bubbles are carbon dioxide bubbles that we forced in there by increasing the pressure. And then we seal it off so it can't get back out. But what happens the second you open the can? Now the pressure here drops like crazy. It drops to the same pressure as you have in your room. What happens to those bubbles? What do they begin to do? They go back to a new equilibrium. And the new equilibrium is all those bubbles are going to have to come out to match what it is in the room. Does it make sense? So what Henry's law says that the amount of a gas, well, this isn't the right side, that the amount of a gas in a liquid is proportional to the amount of the pressure over the liquid. So more pressure, more will dissolve in the liquid. Here there's less pressure, so we have less dissolved. Here there's more pressure, so we have more dissolved. Now what if I use more than one gas? Well, if I use more than one gas, they may not dissolve equally well because some gases are more soluble in water than others are. Of the gases that we're interested in, carbon dioxide is the most soluble. So it's the easiest one to force into the liquid. And that's why usually what you have with soda is carbon dioxide. But you don't have to use carbon dioxide. You could use oxygen. In fact, you may have heard of oxygenated water. Anybody ever heard of that? Well, oxygenated water does it exactly the same way, but instead of using carbon dioxide, it uses oxygen. But there's a problem. The problem is that oxygen is only about 1/20th as soluble as carbon dioxide. So you can't get nearly as much in there. So if you took a can of oxygenated water and a can of soda, this one's going to have a lot more bubbles. And it's also going to be a lot cheaper to make. Oxygenated water is going to be expensive because you have to use even more pressure to get it to go in there. We have one other gas, and that is nitrogen. but nitrogen is practically insoluble. The only way you could get nitrogen into water like that would be to use huge pressures. You have to have very, very, very high pressures to get the oxygen to dissolve, or nitrogen to dissolve in the water. And so when we breathe nitrogen, the pressure is only 760, maybe less. And so almost none of it goes into our blood. But remember that guy who was deep sea diving? Remember, if you go down 33 feet, what happens to the pressure? It goes from 760, remember, to 1520. And if I go down 66 feet, remember, it goes up again. So if I'm out here breathing nitrogen, it does not go into my blood. But if I'm way over here, way under the water, and I'm breathing air from a tank with nitrogen in it, nitrogen goes into the person's blood. And that person becomes almost like a soda. Except it's not carbon dioxide, now it's nitrogen. So they have a lot of nitrogen bubbles in their blood. Well, remember, the bubbles are tiny when you're under the water because they're being pressed on by all that pressure. Remember what happens to the bubbles if you come up too fast? Remember, this is what happens. That tiny little bubble gets bigger and bigger and bigger and bigger, and it can cause hemorrhaging. So the problem down here is the nitrogen. So that nitrogen gets into the blood. So look at it here at sea level. But when you go down, look how compacted it is, and it winds up in the blood. And so if you swim up very quickly, it doesn't leave the blood, it forms these bubbles. And so you get the bends. Make sense? And look at what these bubbles can do. They can cause hemorrhaging. They can accumulate in your brain and spinal cord. They can cause things like paralysis, and it can be permanent because there's lots of dissolved gases down here. Any questions about any of that? So that's Henry's law. Okay, there's one more law, and then we're going to stop for today. This is called Charles's law. Charles's law is very easy to understand. Easy. It's all about temperature. And all it says is that if you warm up air, it takes up more space. So this is how hot air balloons work. So there's nothing special in that balloon, it's just air. But when you turn on this burner, it heats the air. And hot air takes up more space than cool air. Look, if I increase the temperature, these things are going to bounce around harder and bump into each other more often. And so they're going to take up more space. In fact, you can do this at home. It's really easy to see. All you have to do is take like a milk jug or something. Don't put anything in it. It's just got air in it, plain old normal air. Put a balloon over it. And then watch what happens when you put it in hot water versus putting it in cold water. This is what's going to happen. In hot water, gases are going to bounce around, and bounce around. around in here and they're going to push against the walls of the balloon. And they're going to take up more space. When you look at it in cold, what's going to happen is the molecules are going to be a lot closer to each other. And because they are a lot closer to each other, they take up less space. So Charles's law is pretty easy to understand. It literally only says that warm air takes up more space than cold air. So if I don't change anything except temperature, look what happens. Molecules spread out because they bounce around a lot more energy. And when they spread out, they take up more space. When they're cold, they don't spread out as much, and so they don't take up as much space. Any questions about Charles's law? Here are those 4 laws. So there's Boyle's, there's Charles, Dalton, and Henry. So this is a good summary slide. So if you want to look at what each one of them does, you can come at this slide and look at it, and you can see them all the same. And then the very last thing we're going to talk about today is that air moves, air flows. And you already know this. Look, if I take a drinking straw, just a plain old normal straw, and if I blow on one side of it, I'm going to have more pressure here because I'm blowing. I'm creating more pressure in my mouth. And air is going to go this way because there's more pressure here than there is over here. Air flows from high pressure to low pressure. By the exact same token, if I take that same drinking straw, but instead of blowing, I suck on it, now there's less pressure here because I'm creating negative pressure in my mouth. There's higher pressure over here, so air is going to flow this way. If I do it with a syringe, so if you think about a syringe, here's a syringe. You probably played with one of these at some point in your life. It looks something like this. Look what happens if I push on here. This is Boyle's law. Remember Boyle's law? If I push on this and now I make it here, I've decreased the volume. I increase the pressure. What's going to happen to the air that's in here? It's going to flow out because the pressure is higher than it is out here. It flows from high pressure to low pressure. And if I pull back on the syringe, I'm creating a low pressure in here. Now it's higher out here, so air is going to flow this way. Air flows from high pressure to low pressure. If you watch the news and you watch the weather report, you ever watch the weather, the meteorologist, and he's got a map? And look, here's the map of the U.S., sort of. And look, there's this line here, and over here is high pressure, and over here is low pressure. Guess what happens right along that line? What happens along that line is air flows from high pressure to low pressure. The air is flowing like crazy. We call that wind. Does that make sense? Any questions about it? So look, if I fill up a balloon with air and I let go of the opening, the pressure's higher in here and lower out here. So air flows from high pressure to low pressure. Any questions? So those are the gas laws. So that's where we're going to stop. There is one more law. We'll talk about this one when we talk about diffusion. But basically all it says is the diffusion has to do with the amount of surface area and also the concentration gradient. So we're not going to worry about that one. But these are those four laws: Boyle's law, Dalton's law, Charles's law, Henry's law. And then don't forget, air flows from high pressure to low pressure. Any questions? Okay, so don't forget that if you want to go back through this, you can just click on the recording and you'll be able to hear the whole thing. You can also see where I've written on it. Everything's the same. All right, well, I'll see you again tomorrow if you're interested in coming. But tomorrow will be a Q&A. So tomorrow, bring questions. We'll go back through this a little bit, review a little bit, but make sure if you have any questions, bring them with you so that I can answer them. You can also always email me questions and I'll answer them there as well. Okay, so I'm going to stop